In this presentation, I'll be explaining regarding the partial shading. What are the causes of partial shading? What are the effects of partial shading? And how the effect of partial shading can be reduced. These factors will be explained in this one. Now let us see partial shading. In partial shading, certain portion of the solar panel is getting shaded. Therefore, under partial shading operation, the unshaded module of the PV array receives solar radiation at a certain level, while the shaded modules receives lesser radiation, and the generated power also reduces because of the I mean, the radiation that is because of the shading of that one. Maybe the shading of the building, shading of the tree, like that one, falling on that solar panel, there'll be a reduction of power generation will be happening, or that if that is what is called the partial shading. Continuing the partial shading, and here the reason for the partial shading maybe the shadows of the trees, buildings, even clouds also. That is not shadows, the clouds, and dust and dirt, growth of biological breeds, bird dropping, etc. All this will be causing partial shade. And the effect is that, of course, a hot spot formation that will be seen later, and the multiple peaks will be there. Normally, PV, curve, as you know, that one only single peak is, but in this case, there will be multiple peaks comes here. Therefore, multiple peaks in the PV plot will be there. Therefore, multiple peaks will be, and the reduction of the maximum power also getting reduced. Multiple peaks and the reduction in power. That's the effect of the partial shading, and the reduction in overall efficiency. The overall efficiency also gets reduced because of the partial shading. And there are different mitigation techniques, that a global maximum power point methods to locate the global maximum power point tracking methods is there. Then we'll be using bypass diodes, we'll be using. Then separate MPPT for each modules, and the reconfiguration of this PV panel, that is also will be doing. By that one, to a certain extent, the effect of partial shading can be reduced. For partial shading means that because of the shades of the, maybe the building shade in shade, or tree shade, etc., that is falling on the solar panel, the efficiency of that third portion of the solar panel gets reduced, and total efficiency of the solar system, PV system, is getting reduced. That is the effect of partial shading. Continuing the partial shading. Now the power loss due to the partial shading increases as the number of shaded modules in a row increases. For example, if this is a solar panel in which there are 4 into 4, that is 4 solar cells in series, and there are such 4 cells are in parallel. We are numbered as 1 1 1 2 1 3 1 4 2 1 2 2 2 3 2 4, like that. 4 1 4 3 4 4 2 4 3 4. There are 16 PV cells there. This is the one method. In that, but there's no partial shading. Here there's no partial shading, and in that case you will be getting the PV panel, that is the PV plot as power versus voltage plot, that is like this one. Maximum power is extracted, and there is no multiple maxima coming. This is the case, first case. Now, if you second case, if you see that one, see this is shaded. Therefore, this column is shaded. Therefore, the maximum number of rows shaded is equal to 1 here. And if you consider third case, there are shading pattern is different from this one. Though it is shaded number is 4, but the maximum number of solar panels shaded in this row, that is 2 here. This is only 1. If it is 1, that maximum number of shaded panels in a row, what we call that term we call QM. Therefore, in this case, QM equal to 1. Therefore, the corresponding to QM equal to 1, that plot is like this one. You will be getting a plot like this one. Now, if it is QM equal to 2, that is instead of this row here, this is shaded in this pattern, the number of panels shaded in a row, that is equal to 2. Maximum number of panels shaded is equal to 2 here. The third case, we can see that in that third case, when QM equal to 2, it is that yellow one. This is the PV plot as such. Maximum power is reducing. The same time, there are 2 maximums are coming. Here one maximum, and here another maximum is multiple maximas are coming. And the fourth case, we can see that one here again, 1, 2, 3, 4, 5. There are 5 panels are shaded, but in this case again the maximum number of shaded panel in a row is equal to 3 here. QM equal to 3. In that, when QM equal to 3 here, it is the violet one. That is again, this is the corresponding PV plot. Number of, again, maximum power is getting reduced, and number of peaks are again 2. Number of 2 peaks are coming in PV plot. Again, if the solar radiation or the shading pattern is like this one, that is 4. These are maximum number of panels shaded in a row is equal to 4 here. In this case, QM equal to 4. For that, there in that case, this is 1. This plot has that one, the last one, the green one. Again, the maximum power is getting reduced, and there are multiple maximas. Therefore, this QM means that maximum number of shaded panels in a row, that is called QM. Therefore, if Q1, Q2, Q3, Qn are the number of shaded modules of a row 1, 2, 3, and let the maximum of this one, that is called QM, is the maximum number of shaded panels in a row. Therefore, in this case, QM equal to 0, QM equal to 1, QM equal to 2, QM equal to 3, QM equal to 4. As QM increases, we can see that one from 0 to 4 it is increasing. As QM is increasing, the maximum power gets reduced from this to this one, as well as the number of maximum peak is increasing. There are 2 maximum peak here, maximum peak, or the peak points are getting increased here too, here. Therefore, that is the effect of partial shading. Figure relation between the generated power and QM. Generated power gets reduced as QM increases. QM is nothing but maximum number of shaded panel in a row. In continuation to the slide already explained, partial shading. Larger QM, that is, as QM here equal to 0, QM equal to 1, QM equal to 2, QM equal to 3, QM equal to 4. As QM increases, the maximum power available in the panel gets reduced from this to this. Therefore, as larger the QM, lesser the generated power. The solar power, lesser the solar power generated. A solution to this issue of reduced power due to the partial shading is to reduce the QM. If you can reduce the QM, this can be achieved by dispersing the shaded modules to a various rows such that QM can be decreased. If you can, for example, in this case 4, if this is the case, if you can disperse in this fashion, if you are making as a, so that the maximum number of rows shaded can be reduced, then you can increase the maximum power available. That is, we'll see later in the next slide. QM is the maximum number of shaded panels in the row. How? By rearranging the panels, how can you extract the maximum power under partial shaded condition? Now let us see the effect of partial shading on the output power. Here say that first case 1, what we are considering here, each solar panel is generating, of course, here 100 watts. This is 100 watts, 100 watts. Each one is 100 watts. There are 9 panels, and the total power generated is equal to 900 watts, and the corresponding PV characteristic is this one. Therefore, this is an unshaded case. No shading, maximum power you can extract is 900 watts. Now the second, in this one, case 1 itself, shaded, it is being shaded. The last row is being shaded, like each one is shading by percentage wise, it is, each one is, 70 here 100 watts, 100 watt, this is 70 watts. This is 70 watts as such. Therefore, the total power now generated is equal to 100, 100, 100, 100, 100, or 600 plus 70 into 3. 2. That is actually 8 ton watts is there. If it is partially shaded, 70% is shaded. Not 70, 30% is shaded, so that you'll be getting 70 wattage from each one. The total wattage is equal to 8 ton watts. And due to this partial shading, one effect is that maximum power is reduced from 900 watts to 810 watts. Another point is that multiple maxima are created. Apart from here only one maxima, but here 2 maxima comes when this is partially, shaded. The last row is partially shaded. Now, instead of, if you can distribute this shading such that you can reduce QM, that is, so that instead of this one we are making, this is shaded, this is brought to here, and this is shaded in this one, and this is shaded, mean in each row only one panel is shaded. Therefore, QM is now reduced to here, QM equal to 3 and here QM equal to 1. The effect is that, the effect of that, if you distribute this one like by rearranging the panels, if you do like this one, the effect is that the maximum power same as no change, because 6 1 100 watts and 3 1 70 watts. Therefore, 3 into 70 plus 6 into 100, 810 watts. But thing is that the multiple maxima is reduced here. Therefore, the multiple maxima is reduced and the maximum power equal to 810. Now, the case 2, instead of here 70 watts is there. If it is reduced to 40, the shading is 60%, 40 watt is the same argument here. Here, if it is shaded 100 plus 100 plus 100, 600 plus 120, that is 720. It is 720 watt is the, here 720 watt is the, of course in this case the multiple maximas are coming. Now if you are spreading this one, or if you are rearranging this one such that each one, in each row only one shaded panel like this one, you can see that one, there's only one maxima point and that is multiple maxima is avoided. But of course the power is same as this one, that is 6 into 100 plus 3 into 40, therefore 720 watts. Therefore, this is the partial shading effect on the maximum power. And when it is rearranged, what is the effect of removing the multiple maxima? Now, the effect of partial shading is that reduction in reduction in power output, that is maximum power output, and multiple points in the PV, that is multiple maxima points, multiple peaks point in the PV curve, and of course the shift in the location of the global peak, that also gets shifted. Therefore, these are the effect of partial shading. As I already explained in the previous slide, by rearranging the panels, we can make reduce the effect of partial shading. Just to explain that one, there are two types of connection, what we call total cross-tied DCT connection and diagonally total cross-tied connection, that is DTCT is connection. Therefore, here DTCT and TCT connections are solar panel configuration. Now, first take this one. There are 16 panels. There are 1 1, 1 2, 1 3, 1 4, 2 1, 2 2, 2 2, 2 3, 2 4, 3 1, 3 2, 3 3, 3 4, 4 1, 4 2, 4 3, 4 4. Therefore, there are 16 solar panels, and in that one, radiation is coming like this one. This is this type of connection, what we call it as total cross-tied connection. Total cross-tied connection, TCT connection. Now, if you then, this another type of connection, we call it as diagonally total cross-tied. In that one, here what 1 1, and in this one 1 1, then this is equal to 1. Rather than going to 1 2 here, 1 1, 1 2, 1 3, 1 4. Therefore, it is rearranged. These panels are rearranged in a diagonally. That's called diagonally total cross-tied solar panel configuration. Now, if you do this DTCT connection, what is the effect of the solar partial shading as such? Therefore, for example, here same panel is considered here. Here it is 1 1, 1 2, 1 3, 1 4 like that. 4 1, 4 2, 4 3, 4 4 like that. This is the solar panel in which last row is being shaded like this one. Assume the last row is shaded here. Now, if you this is a TCT connection. If you do the same in a diagonally total cross-tied connection like this one, 1 1, 1 2, 1 3, 1 4. Therefore, all these things are changed that one. If you do that type of connection, you can see that one. This row will be shifted in this fashion. That will be shifted here like this one. These are in each row. This one is a partially shaded. This is the partially shaded third one. This is the second one partially shaded. This one is partially shaded. Or we are rearranging this partially shaded solar panels in this fashion, so that in each row there is only one partially shaded solar panel. Therefore, QM now here QM equal to 4, but here QM equal to 1. Therefore, we can see that one under this case, this kind of that is, and when QM equal to 4, here this is that, but two multiple maxima is coming. This is the PV curve of this corresponding to this one. Now, if you do the diagonally total cross type formation like this one, therefore that is distributed. That is, shaded pattern is distributed like that one. Then if you do the same PV curve, then it will be getting like this one. The second one, this is the DCT connection of the PV curve corresponding to DCT. Therefore, you can see from this curve, if you are using a DCT, diagonally total cross type solar panel configuration, the maximum power is increased. Even in the partial shaded condition, the maximum power is increased, of course, compared to the total cross type cross type connection, that is under this. Therefore, here by doing the rearranging the solar panel, you can reduce the effect of partial shading by proper connection. Here the maximum power is increased. Similarly, multiple peaks also eliminated by using DCT connection. For total cross DCT connection and diagonally total cross DCT connection solar panel configurations have been shown here, and the effect of partial shading is reduced by doing DCT connection, DCT connection. One effect of partial shading is the hotspot in the string as such is given. These are indicated, shown as a figure it is shown. These are the hotspots that is forming the solar panels. It's like a hotspot. The reason is that because of the partial shading, one effect is that many modules will not connect, will connected in a string. Many modules will be connected in string. If any module, any panel of this getting partially shaded under a short circuit condition of the string, and the shaded module will become reverse bias. The shade, this portion, this one will become, because of this voltage, or here generated voltage will be less, or because of this one that is get reverse bias, that is being reverse bias. The shaded this one module will become reverse biased, and the power gets dissipated in the poor module. The power will be getting dissipated in the poor module. Poor module means shaded module. The power will be dissipated and the hotspot will be formed in that one. Therefore, that is the effect of partial shading. And hotspot occurs when the solar panel dissipates energy instead of generating it. Normally, solar panel will be generating the energy. But in this case, instead of generating the energy, it is being dissipated in the solar panel. Therefore, that will be producing the hotspot. These are the indication of the hotspot. And the solar cells behaves as they are consuming energy. Rather than generating energy, this solar cell will be consuming energy. Energy will be dissipated. That will be appearing as a hotspot in that one. That is the effect of one effect of the partial shading. Now, apart from the partial shading, the other causes of the hotspot formation is that cell mismatchment. If the cells which occurs when the cell generating different currents are generated in series, if there's a cell mismatchment is there, that will be causing the hotspot formation. Then partial shading, as I already explained, partial shading will be causing hotspot formation. Then open circuit may cause the loss of connection within the module junction box. That will be causing, that's a mechanical connection. Open circuiting that will be causing hotspot. And dirt and sand, photovoltaic panels can become dirty from dust and suspend sand, dirt and the other contaminated impurities during their service life. That will be causing the hotspot formation. And damaged or low quality solar cells, which may occur during the manufacturing, as silicon cells are subjected to stressful process during the rolling, handling and transportation. For damaged low quality solar cell also will be leading to hotspot formation. It's actually damaging the solar cell. Now let us see the role of bypass diode in solar cell as such. Therefore, the bypass diode is a diode which is used to avoid the destructive effect of the hotspot or local heating in series connected modules. In a series connected modules, in order to avoid the hotspot formation, that we'll be connecting a diode across separate. This is a solar cell. Apart from that, we'll be connecting a diode across this, that is opposite to this solar, that is bypass diode. That's called the bypass diode. And bypass diode connected in parallel with the solar module with the opposite polarity. Here, this is the solar cell with opposite polarity. We'll be connecting a diode that's called the bypass diode. And in normal condition, the bypass diode operates in a reverse bias condition. In normally, when there's no hotspot, there's no problem as such. It won't work. I mean, it won't drive any current because that's a reverse bias case. It will work as usual. But due to the hotspot, there's a distraction on this one is there, particular cell is there. Then that current will be carried by the this diode. That, for example, this is a hotspot formed destructive cell as such. That is, in that case, the current be flowing through this diode. It's a bypass diode as such. For in normal condition, the bypass diode operates in reverse bias condition. But if a series connected module is short shaded, reverse bias will appear across it. If it is shaded, reverse bias will be appear across that one, and that will be causing, as I already explained, that will be dissipating all the. That's why, in order to avoid that one, we'll be providing a bypass. By providing a external diode as that. If this reverse bias will act as a forward bias for the bypass diode. If it is reverse bias here, that reverse bias will be acting as a forward bias to the bypass diode, so that the current will be driving to that one. So this is being protected. That particular cell is being protected. Therefore, the hotspot formation is avoided in that.